Alright, let's come back to our impurity functions. We've seen Gini impurity and we started to look at entropy. Well, we saw that the worst distribution you can have, and we call this distribution D, is that whenever you pick a label, all labels are equally probable. Yeah? So that means that your probability of picking a sample with a class K is the same for all K's and is 1 divided by K. Okay? Then we started with the Kullback-Leibler divergence, and we made some calculations and we ended up with this formula here. Okay, so we're gonna start from here, and what we're gonna do, we wanted to be as far away as possible from that distribution. Yeah? So we want to maximize the KL convergence P parallel D, yeah? And we want to maximize that over P. Yeah? If we maximize, we can drop this one here, because that's a constant. Yeah? That's a constant, and will have no influence on our maximization problem. So what we need to maximize is a bit simpler now. We want to maximize the sum of pk times log pk. Yeah? But that's the same as minimizing. We're gonna minimize over p the sum of pk log pk, and we put a minus here. And if we look at this formula here, we have the entropy. Yeah. So what we want to do is we want our leaves of our tree to be as pure as possible, so we're going to minimize entropy. Yeah. Okay. Now let's take a look on how this works in a tree. Yeah. You have a tree where you have S. S is basically all your data points at the start of the tree, and then you're going to do a split. And you have 2 new leaves here, as we've seen. And we want to know what the entropy is at tree level. Entropy of a tree is the entropy of the left here, the left leaf, and this is the right leaf, plus the entropy over the right leaf. Yeah. Now in this case, what do we find? We have 3, 6, 8. Here we have 8 circles, and here we have 6 crosses and 2 circles. Okay, so the entropy of L will be definitely lower than the entropy of R. Yeah? So the entropy of L will be smaller than the entropy of R for the right. Yeah? This is quite obvious. Here you have a pure leaf, here you do not have a pure leaf. Now what is the entropy over the tree? We're gonna have to multiply these two with some weights. And what are these weights? Well, this is, let's call this S to the left and this S to the right. Yeah? And remember, S to the left are all points x, y, yeah, elements of S where the label is left. And the same for R. Okay? And then we defined PL as SL divided by S. Yeah, so these are all points with the label L divided by S. Yeah? And we only look at this leaf. Okay? And you have the same for for the right hand side. So SL are all your points here, SR are all your points here. Okay. Now let's continue here. So the entropy is basically gonna be the entropy of left times PL plus the entropy of right times PR. This is gonna be, these are just the weight factors. So the entropy here we call H of S. Now practically what will we do? Well, it's quite simple. We're gonna look at every split and then take split with lowest entropy. Yeah, this is basically what we're gonna do. So let me maybe change this a little bit here. Yeah, let us have another circle before we have a cross. Okay, so basically what you're gonna do is you're gonna move here, here, here. You're gonna move that line, and every time you calculate the entropy. Let's call this dimension 1, and this we call dimension 2. Yeah, so once you're done with dimension 1, you start with dimension 2. Yeah. The problem, however, is you're gonna have to do all these calculations. You have to go through the whole tree every time you do this. So it's not very efficient. Can we do it more efficient? And the answer is yes. Yeah. The answer is yes. How can we do it more efficient? Well, basically, the way it's gonna work is you have here your situation where here you have 3 circles, here you have a 4th circle, and here you have a few more stuff. Yeah, this is going to be your split one. Yeah, so this piece here is S to the left, and this is S to the right. Yeah, so the P to the, so let's see, the entropy on the left side, yeah, will need to be multiplied by P on the left side. But let's call this SL1 and this SR1. Yeah, and we call this entropy L1 times P L1. Okay. Now, if we move the split to the right here, so we have here split 2. Yeah, so this is the only element that changes. Yeah, so P of L1 is S of L1 divided by S. So, but S of L1 is this piece here, and you see we just add this one. So we're gonna H of L2, yeah, times P of L2. The H of L2 is not gonna change because it's still pure. It's still only circles. Yeah. On the right hand side, however, you take a circle out. So there the entropy So entropy L1 is the same as entropy L2, yeah, on the left, yeah, but entropy R2, yeah, is different from entropy R1, yeah, because you take this one out, yeah, so it's gonna have less circles than with the split one. And basically you see with this formula, the P of L2 is the S of L2 divided by S. Yeah? But the S of L2 is just 4 instead of 3. Yeah? So S of L2 is S of L1 plus 1. Yeah, in this case. So basically what you're going to do is you're going to keep all calculations of the past and just make these type of adjustments. Yeah? So this will be much more efficient.